if you learn how to solve binding energy, you will be good for the, like, 2/3 of this chapter and the rest of your lives, right? Okay, so binding energy, the thing you need to understand about binding energy is it's not something that really happens. We're later going to use the same technique to solve for like the energy of alpha decay and beta decay and stuff like that. This is not something that really happens, but what binding energy is defined as it's the energy needed to take an atom apart, okay? So it's not the energy, it's not energy you have, it's the energy you need to put in to take the atom apart. Now specifically, what we're talking about is if we have a helium atom, a perfectly good helium atom, let's draw it in 1950s style, right? Okay, a helium atom has 2 protons, 2 neutrons, 2 electrons, yes? Okay, we take that thing apart, and when we take it apart, we're going to make it into neutron, neutron, and then we're going to make it into proton, right, with an electron, proton with an electron. Of course, a proton with an electron is what? A hydrogen atom, yes? Okay, so we're going to make this thing into free neutrons, and then we're going to break it apart into a hydrogen atom. Yeah? What are we doing? All right. Okay, so basically, we're going to take this thing, we're going to split it apart. This is not something that really happens, okay? It's just a theoretical thing. It's a way to measure the stability of an atom, okay? Now, relatively speaking, if it takes more energy, can we stop? Can we just have a seat? Okay? If it takes more energy to take an atom apart, okay, then it's a more stable atom. The bigger the binding energy, the more stable the atom. And now to compare atoms to atoms, you have to actually talk about something which is called binding energy per nucleon. Okay? So yeah, there we have it, right? So what we would do is we'd look at how many nucleons we have. Here we have 4 nucleons, and we divide by that. But I'm getting ahead of myself. Okay? Now, to do this, what we're going to do is we're going to compare the mass of this atom here, okay? The neutral atom mass, okay, which you're going to look up in your table. I think it's on page 1064, or I'll show you how to find it on the web. Okay, but you look that thing up in the back of the book, and then this is going to be the taken apart mass. Now, here's the funny thing: if you take these parts, these are all the same things. There's 2 neutrons, 2 protons, 2 electrons. If you put them together this way, they have more mass than if you put them together this way, if they're a helium atom. How did they get more mass? Yeah, mass. Energy has mass. Okay? So what this means is that a moving baseball, okay, has more mass than one sitting still. This guy right now is going to have more mass when I throw it. There we go. Okay? It's a rubber one, right? Okay, how about this? Try this one on for size. This spring has more mass when stretched than it does when it's sitting still. Yeah, a stretched spring has more mass. Not much. This is a few joules, and you'd have to divide by the speed of light squared to figure out the change in mass. It would be unmeasurable, but it's there. This spring, once it touches my hands, gains thermal energy. It has more mass when it has higher thermal energy. That's crazy. Isn't that crazy? And the reason we don't notice this is that, of course, the speed of light, it's the formula is E equals mc squared for this, right? Right? So if you're trying to find a change in mass, it's going to be the energy divided by the speed of light squared. So it's going to be very small. Question?
So we're talking atoms, though.
Yeah.
If you shine a light on like a hydrogen atom or a group of hydrogen atoms, is that amount of energy of the light significant enough to actually affect them to a measurable amount?
Well, the light is going to hit the electrons and make them dance around, right? But I mean, I don't know where we're going with this, but yeah.
So like, I throw a baseball.
Yeah.
Home plate.
Yeah.
Leaves my hand, it gets heavier.
Yes.
And then as it slows down, it gets lighter.
Yeah. It's crazy. As it loses energy, it gets lighter. Not much. Not very much, because we're talking about a few joules. 100 joules divided by light squared is 9 times 10 to the 16th, correct? So it's unmeasurable. I don't think you could have nobody's made a balance that can measure something that small, right? Yeah, relative to a baseball, yeah.
Is it like if it's going faster than the speed of light or something like
No, well, don't go faster than the speed of light. But as you approach the speed of light, yeah, you become real chorkers, right? Yeah, we'll talk about that. But yeah, things much more than double their mass as they get close to the speed of light. Physics. Here we go. So let's just keep hitting the right arrow here. The first concept is what a U is. Okay, a unified mass unit, or an AMU, okay, is 1/12 of a neutral carbon atom with all of its electrons. That's what it means. Neutral means it has all of its electrons. And so a carbon atom is the only one, the only atom, the only nucleus that you don't have to look up. Okay, it's 12. All the other ones are just some weird, bizarre number, and we know it to like 6 places after the decimal point, or more, right? So 1 AMU is 1/12 of a neutral carbon atom. That's the definition of it. Okay, and so there it is in kilograms. And right now, what we can do is we can show, because this is an interesting thing. If you look at this, they're telling us that they're saying that it's in kilograms, and then it's also in energy. So what are they talking about there?
Energy is mass.
Energy is mass, right? So there's a mass-energy equivalence here. So this many kilograms, if you turn it into pure energy, would become this many million electron volts, right? So let's just do this quick calculation. Let's try it on for size, right? This guy, let's go 1.6605 times 10 to the minus 27 kilograms, right? Let's use an accurate speed of light, and here's where we're going to get into trouble. We'll be slightly off, but not much. 2.998 times 10 to the 8th meters per second. Don't forget to square that. So take your calculator and do that right now. Every man, woman, and child. Calculate that. Calculate that. Well, that's closer to the speed of light, yeah. Whoops. Whoops, clear. Second alpha U. Second alpha C. Second alpha U times second alpha. So you guys get something like 1.492 times 10 to the minus 10 joules, right? Okay. Now let's convert this to electron volts, right? So let's divide by 1.602 e to the minus 19. Yeah. And I get 931.5 times 10 to the 6th electron volts, yeah? And you get, I believe, this digit is a 666. I'm getting emotional. Yeah. So here's the difference. The difference is that I'm not using as rounded values as you are. I've got a TI-86. These constants are built into my calculator. So let me just show you what I did. Okay, because I think it's just nifty. Aren't I fancy? Okay, so it went off the screen, but the value stored in C is this value for me, right? So it's 29979, blah, 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 right? Okay, U is actually, I've got a more accurate version of it, so I'm slightly off there. Notice it is 931.5. 931.49. You're going to be slightly off, but that's where it comes from. It's the mass energy equivalent. Okay, so yeah, and this is an important thing, right? So any difference in atomic mass multiplied by 931.5, right, is going to give you the energy released in millions of electron volts. Yeah.
Why did you put 931.5 instead of 9.215?
10 to the 8th, because I wanted to show that it was million electron volts, because that's how it's given to you in your data packet. Does that make sense? Okay, let's escape from that guy. Let's go back here. Okay, so here are some more numbers, and I think you have all of these guys in your notes, don't you? So there we go, blah, 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 blah. Look how fast you're learning. We're not really going to use the electron mass. I just wanted to show you that an electron is roughly 1/2000th of a nucleon. Yeah? So they have a pretty inconsequential mass. I don't want to make them feel bad. And this is not very useful. A mass of a proton is not useful. But we're going to use a neutral atom, neutral hydrogen atoms. That's what we do, is we divide them into neutral hydrogen atoms.